Welcome to Module 1, Part 3. From Chapter 7 onwards, we are going to look at various implementation of heat engines. Chapter 7 is about internal combustion engine. Again, all combustion engines can be either internal combustion, where the fuel is burnt inside the engine, or external combustion. In internal combustion engine, there are two types of engines we will encounter. One is known as the spark ignition engine, which are our typical gasoline powered engine, and compression ignition engine like the diesel engine. So we'll cover the basics of these types of engines, and in a separate module we'll solve a complete manual solution with test calc verification as usual. Our focus will be to look at a real engine and how we model it through an air standard Otto cycle, an idealized cycle which helps us analyze the engine. So the prereq for this module is Module 1 Part 2, where we have discussed and analyzed different kinds of closed processes involving a perfect gas. So let's start from very basic. Just to remind you, let's go to an animation that explains what is a heat engine. A heat engine basically takes heat in and produces net work. If we apply the energy equation to this system, as you can see, you can easily see that the net work that is coming out, heat goes in and comes out. So Q dot net must be equals W dot net, because Q dot net means exactly how much heat is going in, which is Q dot H minus Q dot C in this figure. So this equality is very fundamental in any heat engine. Now, what is thermal efficiency? The net work that is produced divided by Q dot H or Q dot in, you can call it, the rate at which heat is put in. That's the thermal efficiency. Okay, now let's go to the implementation of an internal combustion engine. So this is the spark ignition engine, as most of the cars that you see are based on. Obviously this slide is kind of complicated, so let's go one step at a time. First thing to notice that there are a few definitions first. There are a number of terms introduced in this particular slide. This is a piston cylinder device, and the piston goes up and down. That's why it's called, this reciprocatory motion is called, that's why the engine is called reciprocating cycle. When it's at its farthest position from the top, the piston's location is known as the bottom dead center, BDC, and when it's at the top position, it's called the top dead center. The volume, the distance between the two is called the stroke of the cycle, stroke of the engine, and the displacement, in other words, the volume swept by the piston, is called the displacement volume. On the other hand, when the piston is at the top position, the volume of the gas is called the clearance volume. So if you want to know the volumetric compression ratio, it is not really Vd over Vc, it should be Vd plus Vc, which is the maximum volume, divided by Vc, and that's called the compression ratio R. So this is an important thing to remember from the outset. What is R? Is the smallest amount of volume divided by the maximum volume from which the compression takes place. The diameter of the cylinder is known as bore, and as we have already seen, these valves opens and closes, so the system really is open. So it's a very complicated process. Okay, let's watch the cycle one more time as it executes itself. If you notice that 2 revolutions of the crankshaft, observe the cycle carefully, completes one cycle. In other words, for every two revolutions, there is different strokes that in the cycle are executed. It's a very complicated cycle. So we'll go step by step and show how ultimately this complicated cycle really mimics the simple cycle that we just covered, which is a closed system going through a steady state. So already we saw this is not a closed system. We see the valve opening. Second, it's obviously not steady because the picture is changing with time. The piston is going up and down. So first, let's start by examining each stroke individually. We'll not worry about the analysis at this point, but first let's go over the mechanical part of it. Okay, first the intake stroke. What happens in this stroke is that simply the piston goes from the top dead center to bottom dead center, and as a result, air from outside rushes in because the intake valve is open at that time. The intake valve is open, air rushes in. The simplification is that when air rushes in, the pressure drop is really not significant. You can assume that the pressure outside and the pressure inside the cylinder at the end of the intake process is the same. So in other words, the amount of air that is taken in can be calculated from ideal gas equation of state, PV equals RT, because you know the volume inside is displacement volume plus clearance volume, and the temperature and pressure inside is the same as temperature and pressure outside. Of course, the pressure probably is slightly lower than the outside pressure because there is some pressure drop as the air really passes through the air filter, etc. Important thing to know is it's not pure air. What comes in a spark ignition, in the case of a spark ignition engine, as the air comes in, some fuel is sprayed in the intake manifold, and gasoline being very volatile, it evaporates, and what we get is called a charge. But the amount of gasoline is so small compared to the amount of air that for all practical purpose, you can treat this as air. So here is your first simplification. Even though all these chemicals are produced during combustion, gasoline is present, we will assume the properties really are properties of air. That's why it's called air standard cycle. And it turns out to be pretty good assumption. Okay, so intake stroke is quite simple. In the PV diagram, of course, the volume changes, but the volume V is not a thermodynamic property. The specific volume, small v, actually doesn't change. None of the thermodynamic properties changes between 0 and 1 because it's the outside air simply coming in. Therefore, state 0 and 1 in the TS diagram is the same state as shown here. Okay, let's go and see what happens in the next stroke, in the compression stroke. So what happened in the compression stroke is that both the valves are closed. It's a trapped volume of air now, and the compression takes place isentropically. Well, why is compression isentropic? Let's go and quickly understand that. Okay, let's introduce a new slide here. So why compression is isentropic? If you write the entropy equation for a closed process, again we have done this in chapter 5, the compression is so fast that you can be neglected. As you know, you can run your finger through a flame and your finger will not get burnt. So the system is adiabatic during compression, and in the compression the friction inside can be neglected because the entire volume of gas becomes hot at the same time. There is no internal differences between local states, so therefore there is no gradient destruction. As a result, it's the assumption that there is no thermodynamic friction is pretty good. Therefore, delta S equals 0, which means S1 equals S2. And that's why the process is represented isentropically in a TS diagram. So state 1 is completely known, and state 2 therefore can be found because if the process is isentropic, we know that the volume at 2 divided by volume 1, temperature at 2 and temperature at 1, pressure at 2 at pressure at 1, etc. are connected by some kind of function of k here, function of k here. That's equation 13 that we have been talking about from the PG model, and that's in table J. So if you go to property tables, table J, there's a handout that you should print out, and you go to look at the isentropic equation. So in other words, if you know state 1, which is the outside air, we can find state 2 after the compression process. Okay, so far so good. Next, what happens? After the compression process, really what happens is that the charge is now hot, isentropic. After isentropic compression, the air has been compressed to a higher temperature. So at that temperature, when you just spark, all the vapor, gasoline is ready to burn, and an explosion takes place. Really, the combustion process is very complicated, and in chapter 13 of your textbook, we'll cover that. But the combustion wave propagates so rapidly that for all practical purpose, you can think like the volume hasn't changed, the piston hasn't moved. So all the energy release takes place almost instantly. The system is still closed. The beauty of this Otto cycle is named after Otto, who invented the gasoline engine. The beauty of this cycle is that forget about all this complexity of combustion, volume doesn't change, and we're adding heat suddenly. So that is modeled like a constant volume heat addition process. So we assume that as if heat is added instantly from outside. So this is where Q in is taking place. So the Q in of the cycle takes place instantly. And of course, it is the area under 2 to 3. So at the end of the heat addition process, at state 3, the air is at its hottest, and also the pressure will increase. So as far as calculating Q in, that's quite simple, because we can use the first law for a closed process. Going back, so to model 2 to 3, the constant volume process, again in the TH diagram, 1 to 2 is isentropic compression, and 2 to 3 is constant volume heat addition. The energy equation becomes delta U equals Q minus, of course, delta U is U3 minus U2. And what is Q? Q is same as Q in, right? Because Q in is a positive number, and we know, according to the Wien-Hip convention, sign convention, heat in is positive. So therefore, we can just substitute Q in here. There is no sign necessary. And of course, there is no work, because volume is constant, there is no shaft, there is no electricity, and the volume is not changing. So the equation simplifies as mass times small U3 minus U2, specific internal energy, or Q in is given by M times CV times T3 minus T2. So notice at state 1, we know the volume. Suppose we know the volume of the gas trapped, so therefore we can find mass. CV of air is well known, and if you know the maximum temperature of the cycle, we can find Q in. So this analysis is relatively straightforward. Well, what happens next is that we have the Powerstroke, where we have this hot and compressed air at very high pressure at state 3 expands, pushing the piston down and producing boundary work much in excess of what is required during compression. And that's really called the Powerstroke, producing net work of the cycle. Again, it's a closed volume of air that expands very rapidly, and as you just during compression, as you can assume heat transfer to be 0, even though the air is so hot, we can neglect the heat transfer. So during this expansion process, the process can be considered isentropic. Again, for isentropic, no heat transfer, and no friction inside makes the process isentropic. So from 3 to 4, just like during compression, entropy will remain constant. And to find state 4, it is exactly just the way we found state 2 from 1. If we know state 3, state 4 can be found again from the isentropic relation from equation 13 again of the PG model. So this is how all these states are found. And now what happens is a little bit difficult to explain. At state 4, what happens is that when this hot gas goes there, the pressure, notice is a constant volume line. Constant pressure lines are a little bit less steep. So at state 4, the pressure is still much higher than atmospheric. So what happens is that at this point, the exhaust valve opens slightly, and some of the air, hot air, escapes. In other words, the system loses heat immediately. One of the simplification of the Otto cycle is that we assume that the cylinder, the exhaust valve, even though in reality, in reality the valve opens, we'll assume that the valve remains closed, and as if the valve is closed here, nothing is going out, as if heat suddenly escapes instantly. So in other words, from state 4 is called blowdown. Instead of air escaping, hot air escaping suddenly through a puff, we'll assume that suddenly the heat is lost. So from 4 to 1, the volume didn't change. Instantly heat has been rejected. So we come back to state 1. So that can be again modeled like a heat rejection process, just like we did for heat addition process, Q in, and an energy analysis will produce. Okay, let's do a new slide here for that. So to model the blowdown, this is 1, 2, 3, 4. So from 4 to 1, heat is rejected, and we come back to state 1, and we assume volume remains constant and the system is still closed. And if we again use our energy equation, remember this Q and W's are algebraic, no work obviously, and this becomes mu final, which is 1. 4 is the initial. So notice delta U is final minus initial. From 4 we are going to 1. So it's 1 minus 4. And Q out is a positive number. So therefore Q, which is algebraic, must be negative Q out. Again, remember WinHip is our sign convention. So heat out is negative because heat in is positive. So Q must be a negative number. So that's why we must substitute negative Q out here. So therefore Q out equals M U4 minus U1 mCv T4 minus T1. In other words, if you know the mass trapped in the cylinder and temperature at 1, 2, 3, 4, you can see that you can calculate Q in and Q out. So therefore Q net is Q in minus Q out, we can find, which must be equal to W net. So now that we know how to find W net and Q in, the thermal efficiency is simply network of the cycle divided by Q in. Okay, so now look that with this simplification of constant volume cooling, the exhaust stroke is totally eliminated. What happens in the exhaust stroke is really the rest of the hot gas is thrown out, but 0 to 1 and 1 to 0, the intake stroke and exhaust stroke in this idealized cycle are canceling each other. And really from 0 to 1 and finally from 1 to 0, the systems really is open at that time. Of course, there is work done, but the work done from 0 to 1 and 1 to 0 cancels out. So this part of the cycle is totally neglected in the Otto cycle. So Otto cycle basically is from 1, 2, 3, 4, and 0 to 1 and 1 to 0 are auxiliary processes, the intake and exhaust stroke, that cancels each other. So the beauty of the Otto cycle is that 1, 2, 3, 4, we have a closed system of air that is executing the cycle. So that's illustrated in this. Let's go to an animation here, a different animation. I believe it's in chapter 2. Cycles, closed cycle. So what we've done is that if you go here, notice the Otto cycle can be now regarded like a closed system executing the cycle, where heat comes in instantly at a constant volume and heat is rejected at constant volume. So that's a big simplification for the Otto cycle. But still the question remains that even though now you have a closed system, how can we say it's at steady state? Recall, a heat engine must work at steady state and continuously produce power. Well, that becomes obvious because notice this cycle takes place so rapidly. Your engine RPM is probably 3000 RPM. In 1 minute, the crankshaft turns 3000 times. So if you take a picture and blur the picture for a second, for instance, then you will see so many cycles. On the average, you will see as if heat is coming in continuously, heat is being released continuously, and network is produced continuously, so that the system behaves in a steady manner. In other words, if the picture is taken over a reasonable time, that is, it's not a really instantaneous picture, but the exposure time is, let's say, half a second. And who cares about what happens in a millisecond? We are happy whenever we take a measurement, there's a minimum time of measurement. So if our time of interest is, say, over half a second, there'll be so many cycles executed, it will be, for all practical purpose, a steady engine. So if n is the number of cycles executed every second, as you can see, n times q in is the q dot in. So we can simplify the equation as q dot net then equals n times q net. Similarly, w dot net will be n times w net. We have shown that q net and w net are equal. So if n is the number of cycles executed every second, to find the rate of the power produced or the net heat in every second, all you have to multiply that is by number of cycles per second. And that's where there's a catch. You have to understand that to find how many cycles is executed by reciprocating cycle in a 4-stroke cycle, which is your typical gasoline or diesel cycle is. In a 4-stroke cycle, the intake and exhaust stroke, remember, do not participate in the actual thermodynamic cycle. So therefore 2 strokes are almost wasted. So out of the 4 strokes, in a 4-stroke cycle, out of 2 revolutions, you get 1 cycle. Again, if you watch the reciprocating cycle animation, it becomes clear that every 2 revolutions of the cycle, we produce 1 power stroke. So the number of cycles and the RPM of the crankshaft, there should be a factor of 2 in between. So if the crankshaft is cycling at a rate of capital N per second, so this would be number of cycles per second. And just one more thing, that this is all based on 1 cylinder. If we have more than 1 cylinder, if you have multiple cylinder, suppose your car has 4 different cylinders, then ultimately the total power will be given by w dot net total will be number of cylinder time w dot net from each. Is kind of commonsensical. So if you may write down this formula here, that W dot net total of a car engine will be number of cylinder times W dot net per cylinder. And what is W dot net? That is number of cycles per second times W net produced in each cycle, and that's equals N over 2 W net, where capital N is number of revolution of crankshaft per second. We'll mostly base all our calculation on a single cylinder. So this and that, where W net is kilojoule per cycle, where W dot net will be kilowatt, because we are multiplying this by cycles per second. And that's how we get kilojoule per second, or kilowatt on the right hand side. So if we have to summarize, we have a summarization slide. 7B Otto cycle. Again, notice from 1 to 2 we have the isentropic compression, and 2 to 3 instantaneous heat addition, constant volume. That's why it rapidly goes, right? Instead of combustion, we are adding heat instantly from outside. From 3 to 4, again, we have isentropic expansion. And 4 to 1, in the blowdown, we really have a constant volume, instantaneous heat rejection. The piston barely moves, and we reject the heat. As we saw in chapter 5, the meaning of a TS diagram, the graphical meaning of heat transfer, is in an internally reversible process. The area underneath the TS diagram, under the TS plot, represents the heat transfer. That's why Q in is the shaded area under 2-3, and Q out is the shaded area under the 4-1 branch. So the net area inside is proportional, as you can see, to Q net. Similarly, W net can be shown to be the net area inside the PV diagram, and they must be equal, as we have already proven. But to get the formula for efficiency, instead of calculating W net, it's much easier to calculate Q in and Q out, as we saw in our analysis using perfect gas model. So substituting those formulas that we just developed from the energy analysis, mCv T4 minus T1 is the energy Q out, and mCv T3 minus T2 is the energy that is in by heat. And we get a simple formula for the thermal efficiency. You can even simplify further if you recognize that by taking T1 and T2 common outside this parenthesis, and realizing that state the isentropic relation, that T2 over T1 and T3 over T4, they are a function of volumetric compression ratio as given by equation 13. So if you go to that equation 13 of the PG model, you can show that these temperature ratios are equal, and therefore this terms cancels out, and we get a very simple formula. Again, T1 over T2, we substitute compression ratio, volumetric compression ratio to the K minus 1, and recall that value of K is 1.4. So the thermal efficiency of a internal combustion engine executing spark ignition cycle or Otto cycle is given by 1 minus R to the K minus 1. This is only true for cold air standard cycle. And we'll see that it will become almost obvious why increasing the compression ratio, as the formula says, if the compression ratio is increased, cycle efficiency must increase. And we'll see why it makes sense once we understand the TS diagram and its significance. But we'll do that after we solve a problem. So we'll just want to solve a simple problem, verify it with test calc, and numerically show that if we increase R, the efficiency goes up as this formula suggests. And then we'll come back to the TS diagram and qualitatively try to predict why the efficiency should increase. And that will lead us to understand diesel cycle, why diesel cycle is more efficient.